We started talking about Model 3, and so we will continue with this one. Model 3 is an extension of what we've been doing, but now we're going to compare two means. The only difference is now there's two populations. There are two means. There's mu1, there's mu2. There's sigma 1 square, sigma 2 square, and this is unknown. As usual, and we have answered this many times, the point estimate for mean is always the sample mean. That makes sense. The point estimate for variance is the maximum likelihood estimator of the variance, or the MOM estimate. Both of them. They are same actually. Can you use the sample variance? Yes, you can. But there's a slightly different denominator. All right. Okay. Before we can do any assumptions, does anyone remember what do we assume? We assume that the two populations actually possess the same variance. That is an assumption. And does anyone remember how do we go about at least looking at how to evaluate whether this assumption is valid or not? What do we need to look at? What graph can we look at? Does anyone remember? The last thing we said last week. What graph can you use that will help you check whether this is a reasonable assumption that the two have the same variances in the first place? You remember we discussed this at the end of last week. There's a simple plot that you can follow. You plot what is called the normal probability plot that I showed you before. Those dots, there's a contour. Remember that one that we showed you? If you find that the two populations plot, the two samples of the two populations, if they have similar slopes, then that is a reasonable assumption that the variances are the same. It's not proof, but it at least tells you that this is a reasonable model assumption. So one thing I want to let you all know about statistics. Some things in statistics is a mixture of proving things and also a mixture of whether a model assumption makes sense or not. The model assumption sometimes cannot prove this. Are you willing to accept that the two populations have the same spread? One way to check whether that's reasonable is to plot the graph, but the plotting of the graph is not a proof. All right. So if you are willing to accept that the two things have the same population variance, a reasonable way to estimate that is S squared. And if you've been in any of my stats classes before, you know I've talked about this many times. How do you prove an estimate? You take the standard deviation squared of population 1, sample 1, multiply by the sample size less 1, add up all this thing and divide by the total sample size minus 2. All right? So that's how you find S squared pool. Now, here is a result, and this is new for today. A fact from probability theory. If the samples are independent, again, you see, not only must each sample have data that are independent, the two samples are also dependent. So there's independence at every level. First of all, within the population, take everything is independent. The two populations themselves are independent. So a lot of independence is needed. If you have that, I want you to guess. Just guess. What do you think is the distribution of this one? This is an extension, right? Today, we just talked about a proof where you have to just y bar minus mu over s over root n. If you remember, we just showed that one. So anyone want to guess? What is the distribution of this guy? Can you give me a letter? Very good. Yes, what he said. So it is this. This has a T. Good. That was the first correct guess. And it is this number of degrees of freedom. So I hope it is reassured. So I hope this is a little bit clearer now why the degree of freedom is like that. I want to spend a bit of time talking about it. Where does this come from? Did you see your S pool? What's in the denominator? The denominator of S pool has an N1 plus N2 minus 2, right? That's where it came from. So can anyone tell me why this is consistent with what we just showed just now? I think I still have the slides. See, we showed what? We just showed that x bar minus mu divided by s over root, and this is Tn minus 1, right? Can anyone see a link between when this was just one population, this was Tn minus 1. Anyone can see the connection. Why does it make sense? I mean, I know we proved it, but can you see intuitively why this is N minus 1 and why this connects to this result that when you have S pooled now, it's N1 plus N2 minus 2. Anyone know what I'm actually trying to say? Is it consistent to you why this has to be N minus 1 degrees freedom when there's only one population? Anyone can see the connection? How is S found? When you find the standard deviation of one sample from one population, what's the divisor? The denominator is N minus 1. See, when you find a standard deviation for one sample, the denominator is N minus 1. So you see, this follows the denominator of this. That's basically what I'm trying to say. The degree of freedom is the denominator in the finding of the S. So when you have two sample problem, you now use S pool that came from two samples, and the degree of freedom follows the denominator for this connection, like that. Right? So it's quite important that I want to make cheat sheet for the exam. So this kind of result you should write on the cheat sheet so that we can know, oh, this guy is distributed as a T. T unique degree. Unless, of course, you can memorize this. Okay? We will use these facts, of course, when we try to find confidence intervals and things like that. Okay, now here's an important note. A lot of people have asked me every time, what if I don't use S2? Do you see the difference between this formula and this formula? They're not the same. This is using the full estimate of S. This is, I just take the separate S1 squared, S2 squared, right there, just dump it in. Now, numerically, this number and this number, especially if the sample sizes are quite close, and if the S values are quite close, these two will be numerically quite similar, but they're not the same thing. A lot of people have asked me in the past, in this school especially, does anyone know the distribution of this? And the answer is no one knows. It's not, I mean, you can derive it, but it's not T. When you take separate standard deviations and dump it in, this is no longer T. There's no known distribution for this one. I think it's something that no one has bothered to derive because it's quite close in probability to what you have for T, but it's not. That's the point. It's not worthwhile working out this one because it's quite close to T, but it's not exactly T. So you see, when people use the S1, S2 separately, they treat this as if it's T distributed. It's not like this. And what degree of freedom do we use? Does anyone remember this from class last time? If you don't, I will just show you. The default we use in class is we take the minimum of the two sample sizes minus 1 as the DF. Notice this is not the same thing as doing this. This is you add the two sample sizes and minus 2. This is the two sample sizes, you find out who is the smaller of the two and that's one. Again, is there any logic here? No. There's no. That's right. And when people ask me, they say, why? I said, there's no why. This is a compromise. This actually is being what we call conservative in statistics. Because when the degree of freedom, I mean, who's going to have a smaller degree of freedom? Is this degree of freedom smaller or is this degree smaller? Is this degree of freedom smaller or this one smaller? This is smaller, right? When your degree of freedom is smaller, you'll end up with a wider confidence. Basically, you're being punished. You're forced to have some kind of degree of freedom, so people just dump this in, and there is no statistical justification other than to make it more personal. That's it, right? So if anyone tells you, "Is this T?" I want you, any student of mine who reads this class should know the importance of being able to tell you, but this is not T distributed. Right? A lot of people think it is. It's not right. If you use S pool, yes, but if you don't, no. All right. Okay, so here are some rules. I will let you take a look. You can take a picture of this. You can, of course. You can copy down. Here are what you do to okay. So let's forget about it. Now SP is a shortened word for SO. We go back to the using S-pool. Okay, that was just a short aside. If you use S-pool, everything is nice. You do have t-distributions exactly. Again, I hope this formula is familiar from all the stats classes that you have done with me. You want to find a confidence interval for difference means you use the two sample. You use an appropriate quantile, a multiplier, if you remember. Remember the A, B, C, D, E thing in class that we used to do, all right? So you take the two means, you want to do a 1 versus 2 comparison. You take the mean of the first sample, mean of the second sample, some quantile. Notice the degree of freedom. The degree of freedom follows the S-pool quantity. Just the hint. The degree of freedom you use always follows the S part. Let me see if I can flash back to long ago when we were doing for one sample. When it was just one sample, I just want to go back to the notes. Get some time away. I'm just trying to show you the consistency here. Where is it? Confidence interval. Yeah. See, when we try to form a confidence interval and we're taking one sample, we use a Tn minus 1. Right? This T here, that time, because this was a one sample problem, the degree of freedom here was N minus 1. Right? Here now, because you are using a S pool, the degree of freedom follows the degree of freedom, the denominator of S pool. That's what we take away. So how do you test hypotheses? If you want to test whether mu1 is equal to mu2 versus mu1 is greater than mu2, this is a right side test. So you go and compute this test statistic, which I hope looks familiar to you as well. You take the two means and divide by this. I don't know whether you realize one way to study statistics is, do you see that if I take this part, this is on. If I take this part and put it at the bottom, then I get my t ratio. So it's always like this. Estimate, multiplier, some kind of standard error. So if I take the standard error and divide by this, I get my t statistic. They use the same ingredients, So you take this and you compare this to a standard significance level. If you do a significance level and you pick alpha, then you need to find the alpha quantile. And now the time has come for me to show you the table that I will give you for this course that you use. I just want to show it to you for once. All right. Okay. So what is going on? Okay. If you go to our page, you see there's a t distribution table, critical values. Okay, click on this one. Okay, let me explain. This is exactly the table that you need, right? And I'll give it to you in the exam. So you see, how do you find the significance level of, okay, so if I pick famous one 5%, you pick 5%, and then your sample size, let's say n1 plus n2 minus 2 is some number, let's say it's 41. 40, all right? Let's say your n1 plus n2 minus 2 is 40, and your alpha that you pick is 5%. Go to this table and go to 40 degrees of freedom, which is here. And then you just check, where is the 5% point? Shaded area is alpha, so go to 5%. It's the second column. Then 1.684 is your critical value. That's how you check. The picture helps you see that when you want this area to be 5%, you go to 5%, and then you have 1.684, like that. So if you have all this, this just tells you that if I have detecting H naught at a 5% significance level, when this exceeds 1.684, if I have 40 degrees of freedom, how you know you check it out. Finding the p-value is a little bit trickier. This one is, what kind of t did you get? I mean, there's some examples coming up, so I will show you, right? I think I'll let you copy an example and we'll take a look at it together. This is the other side. If you do a one-sided test on the left side, then you go to the left side. P-value is on the left side area. If you do a double-sided test, then you need to look at the absolute value. And the p-value is twice the area of the two tails. So you all know this, right? When you have a two-sided test, you have to draw this picture, but you put two tails that you want the area. So because of the symmetric nature of the t-distribution, you find one side, multiply it by 2. You'll get more practice when I give you some homework questions. Right. Just remember, p-values are areas. Whether the area is on one side or both sides depends on the alternative hypothesis. If your alternative hypothesis is one-sided, then you only put one-side area. If your alternative is two-sided, you put two sides. That's it. Okay. I think some of you work in the math lab, right? I think a lot of students will be asking you these types of things. Okay. So it's good to revise these anyway. Okay, here's an example. Okay, we want to compare the mean lifetimes of springs at two levels of stress. So I hope you realize the two levels of stress become the two populations. Okay, this has introduced two populations into the picture. We are going to assume normality for the spring lifetimes, okay? Both samples are of size 10. It doesn't matter that the samples are small because we are assuming normality. If you are not assuming normality, this is going to be a problem. Sample is very, very small. But if it's normal, we don't care. It can be as small as you want, but it's normal, then it's fine. So we have two samples that are small, 10 size 10 each. Here are the two means. Here are the two variances. And we want to do these tests. Yeah, just do a demo, right? We want to test this hypothesis versus this one. So this is one-sided, greater than. Level is always 5%. Then we are also going to test this as a double-sided test, same level 5%. We are going to construct confidence intervals. And I'm also going to ask you to construct a confidence interval if we don't assume that the two variances are the same. All right, so everything in white. So how do we do this? Okay, let's look at number 1 first. First, we calculate, of course, this statistic. You need to find an S-squared pool, which is just arithmetic. You take the two S-squared values from the two separate samples, scale it by sample size less 1, less sample size less 1, divide by 18, because 10 plus 10 minus 2 is 18. That gives you your SP, and then you just dump in all the sample size, sample mean, and I get 2.7. So with 2.7, what does that tell you? Now, this is where I want you to realize there are two ways to test hypotheses. One is using a significance level. That's the first way we're going to show you now. We fix the significance level at 5%. You go check the table, you will see this is 1.734. I'll prove it to you. Let's look at it now. When your degree of freedom is 18, and you want the 5% area, do you see 1.734? Right? That's where it comes from. So that's why this becomes the critical value. And it always helps to draw a small picture. 18 degrees of freedom, this is the critical value, 1734. So of course you reject it now at this level. Why? Because your t value was outside here, it's 2.7. Cross the 1.734 already, so you reject it. At this significance level. Right? This is using the significance level approach. Immediately, I want to show you, can you identify the p-value? Why do I say it is between this and this? I'll show you. All you can see if you use the table is between. Why? Because your t statistic was calculated at 2.7. You go back to your table and check. Okay, at 18 degrees of freedom, where is 2.7? 2.7 is between these two numbers. You see that? 2.7. And these are between what? Look at the area between 0.01 and 0.005. That's where these things are coming from. Okay. So, as I said, it's very good that you get all these revised because very soon I'm going to be teaching these things and students are going to be asking you. It's very hard for intro-step classes to understand these things. It takes me a lot of effort to teach. I hope this is not too difficult for you, right? It's just looking at the table. Just knowing the difference between when you reject the null, you reject the null if this one exceeds the critical value. That this is actually, some people like this approach because it's just easier. P-value approach is different. P-value is I don't have a significance level. I just report to you what's the area after the critical. Okay, let's look at another one. What about if the test had been two-sided? All right. Okay. Here's where you have to be careful. If the test is two-sided, anyone know why the critical value needs to be changed? Why does it become 2.101? If the alternative is two-sided, then if you test at a 5%, you have to divide the 5% area by 2. That's why now I'm looking at 0.025. That's why the critical value is changed. Do you see this central point? Right? I told you in the example. We want to test these things in a variety of alternative hypotheses. The first alternative hypothesis was one-sided. One-sided is the easiest. Two-sided, a little bit more confusing because if you still want to use 5%, but it's two-sided, you have to share that area with two sides. So you must put 2.5% on either side. That's why this critical value has changed. Do you still reject the null? Yes, because 2.7 is still more than. Anyone know why the p-value is between twice this and twice that? We didn't have to change this part. You know why? Haven't we established that at 2.7, the area after 2.7 is between this and this? Now you must say you multiply by 2 because when you do a p-value for two-sided test, it is the area on the right side plus the area on the left side. If you look at my slides here, see? When you do a p-value for two-sided test, it's twice the area of both sides. Right? Okay. What about confidence intervals? Quite easy. To form a confidence interval, all you need to do is use the rule. You take the difference in means. Why am I using P18.025? Remember that confidence intervals are always in the middle. You must take the significance level and divide it by 2. So if you want to form a 95% CI, you must say, oh, 95% CI is middle area. So I must have 2.5 on either side. That's why there's 2.5%. Right? Confidence intervals are not one-sided, they are in the center. So you have two sides to think about. And that's it. So go use your table and get it. If we don't assume equality of variances, and we use this funny formula that I told you is not true, it's not T, then anyone know why this is 9 now? Why is the degree of freedom change from 18 to 9?
Because you are using S-pool instead of just
Oh yeah, because we're not using S-pool, we're using a minimum of 2 samples at a time. Here we were using S-pool, correct? We are using S-pool here, so it's 18. But now we are not using S-pool, we're using separate standard deviation. So you see the separate, the two sample sizes, the smaller of the two, that's one. Can you see, is there some justification for not assuming a common variance? I will say there is, Look at the two variances. One sample had an SD of 33.1, another one had an SD of 42.1. They're quite far. Together, they form a pool less than 38.3. So it's not entirely unjustifiable doing this thing. That's it. So this is using separate, and you see the price that you pay, look at how much wider this confidence interval is compared to this confidence. But that's basically what. Okay. So that's how you get an approximate CI. These are very practical things that people may ask you next time how to do. Just remember the underlying assumption, normality of the data, and then independence, not just of the data within the one population, across the two populations as well. If you have all these things, then you can. And then the third assumption, if I have common variance, I use S pool, which leads to an exact P calculation interval. you like don't have common variance, or you can see that they're very far apart, then you use the separate variance formula and you are forced to use a smaller degree of freedom. It's no longer this is a compromise. It's not an exact confidence interval anymore. Alright? Okay. So here, these are just the things I was just saying. If the data are assumed to come from a normal distribution and they are independent with common variance, then the pooled variance has a chi-square with n1 plus n2 minus 2 degrees of freedom. Inference for sigma squared. Now we're going to talk about inference for sigma squared. If I know that this is chi-square n1 plus n2 minus 2, then you just proceed by using that degree of freedom. Inference proceeds exactly as in model 2 but with a chi-square. So here's another table for you to look at. You should immediately compare it to what you know for when it was just variance of one population. Remember, for one population, we didn't have n1 plus n2 minus 2, we have n minus 1. Well, now it's using this square rule. It came from two populations. You scale it by n1 plus n2 minus 2. So when you study these things, compare your notes. Look at the old slide. So when I give you inference of sigma squared on one population, if it's one population, you use just s squared from that one population, from that one sample, and you scale it by n minus 1. Now there's two populations, two samples, so you use n1 plus n2 minus 2 like that. You need to find this chi-square L and chi-square U. What are chi-square L and chi-square U? These are just the lower and upper limit depending on the percentage of the confidence interval you form. If you want to form a 95% CI, find out what these two should be so that you have 2.5% here and 2.5%. That's it. Same old thing again and again and again. Okay? The key to studying these things and not getting mixed up is to always compare to what you know from a simple case. When you have one population, you have only one standard deviation, everything was just n minus 1, n minus 1, n minus 1. Now that you replace the S square pool and you pool the two sample sizes together. I think I have an example I will give you, and I will get to that. Okay, let's look at an example. We have two populations of springs, right? We are going to use the same numbers. Your first population, your first sample had a standard deviation of 42.9. Second one is 33. If we assume a common variance, we can of course find S square pooled, and you find that it's 1468 and all that. Okay. So what do? You calculate C18 n1 plus n2 minus 2. That's 18. S square pooled over 35 squared. Okay. So why? This 35 is because of this one, right? The W statistic that you want. This is the thing. This hash here. You put in the number that you're now saying sigma squared is. If I am trying to test whether sigma squared is 35, then you put 35. That's the logic behind what's going on. So you put 35 inside and square it. Right? You form the W statistic using this definition. N1 plus N2 minus 2 SP square over whatever the null says sigma square is. So you just dump 35 as your sigma, 35 square as your sigma square. Calculate this. This is an important number. Now what's going on? Everything is going to be based on a chi-square 18. a chi-square 18 with 2.5% area on both sides, then your limits are 8.231 and 31.526. I've also indicated where my 21.57 is 31.576 here. So we do not reject the null at 5%. Why? Because 21.57 is very much within the acceptable range. The value is this area that you want. It is a one-sided crest. This is a two-sided test. So two-sided test, you have to follow this rule. Find the smaller of the two areas, and then you multiply by 2. All right? How do I know that this area is between 0.1 and 0.9? You go to the chi-square table. I'll show you. So on our page, we have the chi-square table as well. So we were on 18 degrees of freedom. And the W that we calculated was how much? We had a W value of 21.57. So you can see that 21.57 is sandwiched between these two numbers, like that. If you are sandwiched between these two numbers, this just means that the area to the right side is something between 0.1 and 0.9. All right? So that's how I know the area to the right side of 21.57 is something between 0.1. Therefore, the rule is the p-value is take the smaller of these two areas. If you look at the rule, let me just go backwards again. You take the smaller of the right side and left side areas and multiply by 2. It's the two-sided test. So we know that the area on either side is this side's area is something between 0.1, right? So we know that, let's say it's 0.2 or something like that. Then you take twice 0.2. That's why we know the p-value is more than 0.2. That's all. So you don't reject the null, right? P-value is very big. So that's how you carry out a hypothesis test. Confidence interval, same old thing. You take 18 SP square and you divide by, now this is actually easier. You divide by this 31.526 and 8.231. Why? Because these are the lower 2.5% and lower 97.5%. Okay. I will give you a homework to practice these things with numbers so you try. Right? You just divide the correct compound and get the answer. This is just one thing I want to mention. If you have formed a confidence interval for sigma squared, if you want a confidence interval for sigma, you know you need to square root both sides. It's okay. So once you have found a confidence interval for sigma squared, taking square roots will give you the confidence interval for sigma. This is easy. Right? Okay, how do we test the assumption that sigma 1 and sigma 2 are the same? All right? Because I told you, looking at the normal probability plot is just the first step. It's just a picture way of doing it. There is a proof, if you want, you can test this hypothesis, but we have to learn something else. Okay. So first of all, what are some assumptions from the start? We always assume that we have independent samples from normal. I can't stress this, I think I've said this so many times already. These tests start on the assumption that your samples are independent, they are both normal. Right? I just drawn a picture. There are two populations. They have unknown variances. Okay, here's where we're going to introduce another distribution. If you look at this ratio now of the two standard deviation squares, ratio by the S sigma 1 square, this has what we call an F distribution with two kinds of degrees of freedom. So don't freak out about this. I will show you how to read the table as well. Okay. When do we use this? We use this to test the assumption whether this is reasonable or not. So as I said, the picture test is just a preliminary way to look at it. You draw the normal probability plot of the two data sets. If you get the two lines roughly parallel, then you're good. But that's just an informal test. This is the formal way of testing it. You need to use the F distribution. So how does this work? So first of all, what does the F distribution look like? They all seem to look like the same thing. They look like chi-square, but again, this comes from a chi-square, but it's not exactly, okay? Oh, the density is getting worse and worse. Now, the interesting thing is, do you know that the F distribution is quite young? Okay, it's not a very old distribution. And I think I must tell you this story again. It was actually, the word is derived by, okay, it's not discovered. The F distribution, this density was derived by George Snedeker. And George Snedeker was a faculty member at my grad school. Okay. Not when I was in grad school, he was already dead already. But that's why my building in Iowa State, where I did my PhD, is called Snedeker Hall. It's in honor of George Snedeker. So when was George Snedeker doing these things? I think it was in the 1940s or 30s. So it's not, this distribution is not even 100 years old. Do you know how rare it is? You know, the math that you learn in this school, right, a lot of it is very old. Calculus is very old already. This is quite a young distribution. It hasn't been known for like hundreds of years, not even 100 years. So this is actually quite, all right? So he derived this. Right? Anyway, so, okay. So first thing is we are going to show you how to read the F table. Okay. I have also put an F table into our page on Moodle. Let me show you what it's like. The F table is a very inefficient table. You know why? Let me show it to you. The F table is very inefficient because there are 2 degrees of freedom you need to worry about. First of all, do you see this? There is the numerator degree of freedom on this column. There's also the denominator degree of freedom in the groups. So you must check 2 degrees of freedom. How do we know this? There are 2 degrees of freedom because you can see in this definition there is V1 and V2, or U1 and U2. That's the problem. So there's 2 degrees of freedom. Where did these 2 degrees of freedom come from? They actually came because of the ratio of 2 S things. This S1 squared upon S2 squared. S1 squared is actually chi-squared with N1 minus 1 degrees of freedom. S2 squared is also chi-squared with N2 minus 1 degrees of freedom. So it is because of the 2 different degrees of freedom that come from the 2 different chi-squared. That's why there are 2 degrees of freedom in F distribution, because of the ratio of 2 chi-squareds. So how do we read it? Okay, so let's do a simple example first. Let's say something has an F3,5 distribution. Can you find the critical value so that the area after that is 5%? So look at the solution. Look at table A9, that's the F table, with numerator df3 and denominator df5. All right? So where is that? 3 and 5. Huh? So the F table, numerator 3, so column 3, denominator 5, so here. So we are looking at these values here. Do you see the 0.05 critical part, right? The 0.05 area will happen when these are at 5.41. Do you see a 5.41 here, like that? So that explains why I got 5.41 as the critical value. Okay. This table gives you areas on the right side. So you don't have to convert. Okay. Now here's something that is different. Can you find another number so that this area less than this number is only 1%? Okay. you will find that 1% on the F table, all right, is here. Okay. So what you need to do is you just check. Okay, first of all, you need a 1%, right? Okay, you want to know what is the area so that it is 1% after it. Okay, but here you are looking for this point, so it's 1%, which means to the right of this is 99%. If your area less than something is 1%, then to the right is 99%. This table doesn't have 99%. This table doesn't have 99%. So what do we do? It has 1%, but it's right side. There's no symmetricity to help you. So you need one extra piece of information. First of all, it is a rule that says the F distribution has a unique property. And FV1, V2, lower percentage point is the reciprocal upside down of the corresponding FV2, V1 upper percentage point. What do I mean by this? If you want a lower 1% point, what you can do is get the 99% upper percentage point and then invert the two. So you are still looking at an F35. You're interested in F35. But if you want a 99% area after a certain point, you don't have that on the table. But if you look at F53, if you reverse the order, F53, you can find the upper 99%, the upper 1%. That gives you 28.24. I'll show you. If you go instead to an F53, 5 and 3, do you see the 28.24 here for 1%? So let me get things straight, okay? This 28.24 is the value after which on the right side your area is 1%, which is the thing that you want because the 1% area to the right is equivalent to, is equivalent to the 1% area on the left when you are looking at an F35. So in other words, F35 and F53 have reciprocal values for where the 1% area is. So I'll go through this again. You want to actually talk about F35, you are looking for the 99% right side area. This is left side is 1%, so right side is 99. Table doesn't have. But a table has 1% area on the right, and the good part is the relationship is the lower percentage point and the upper percentage point are connected by reversing the degree of freedom and take the reciprocal. So go and find the 1% area on the right for an F53 first. That gives you 28.24. Then the thing that you want is 1 upon that. It's quite complicated, but it's actually not. The most straightforward is you have the area that you want and it's right side. Then you just go straight to the table and get the answer. But if you want a particular area that's not available on the right, then you need to find the reciprocal of it when you flip the 2 degrees of freedom. Like that. That's what's going on. Okay. So again, in R, you can get the exact number. You don't have to use a table, but I'm just showing you that because I will give you table in the exam, so you can use. All right. So how do we use this to test hypothesis? To do a formal hypothesis test for whether this thing makes sense, you need to construct this F statistic and you compare it to the F distribution that we just talked about. So let me give you an example. Okay. So we have 2 kinds of material. Basically, the sample size is, the first one is 8, second one is 10. Here are the 2 standard deviations. Quite different by R, right? Okay. We want to do this test at a 0.1 significance level. Okay. So remember, the test is, are these two populations having the same variance or not? Or are they different? So this is a two-sided test. Okay. The test statistic is the ratio of the two sample standard deviations. Okay, so it's the ratio of the two sample standard deviations like that. Okay, so here comes the calculation. Have a look. First of all, why am I looking at an F79? I'm looking at an F79 because that's the sample size less one, sample size less one. Okay, first of all. If you look at an F79, we need to find out when the significance level is 10%, what's the 5% point here and the 5% point here. Okay, so you can get this from the table. I'll show you. 3.29 is the easier one to get because we know that the table gives you right side. Okay, so have a look. F79, F79. Right. So do you see at 5%, there's a 3.29 here. Okay, 3.29. So that explains why we know this number is 3.2. Unfortunately, we don't have when this area is 5% on the left. Because if this area is 5% on the left, then the right side area is 95%. We don't have tables like that. However, we know that we have that kind of thing equivalently for F97. And F97, if you check the table, has the 3.68. And so we know that this guy is 1 upon is a reciprocal of that one. Basically, this is to establish where the critical values are. Why have I put some things in red? These things in red are what are code that you can use to get the quantiles if you don't want to use a table. I'll show you. F distribution, Q is quantile. These are the quantiles that you want. So QF, you can either use 0.9579 or you can go with 0.0579 and just say lower tail equals false. Both are equivalent. I do recommend that you also take down the notes for when it's using R because it's useful, right? You might not always have the table with you. So you calculate your F statistic finally, you find that, oh, I got 0.057. 0.057 is outside the acceptance region. It's gone into the rejection area. It's less than this. So you reject no. Are you surprised that you rejected a no? Look at the two standard deviations. One is 3.5, one is 14.6. They're very far. So even though the sample sizes are very, very small, but we assume normality and everything, these are too far away from each other. That is why we rejected them. There is evidence that the two variances are not the same. This is how you do a formal F test for testing equality of variances. So you can see that it's quite important that the general idea is quite strong in your head. When you want to do a hypothesis test, of course, first of all, you must write down what the null and alternative hypothesis are. Once you have the null and alternative hypothesis, you need your test statistic. You need to know the distribution of these things. Like that. Then you have to set up the critical region. Where is it? So draw a picture. We know F distribution looks like this. Just get all the critical values. Either use R to get the critical value or use table. Okay. As I said, there will be more for you to practice and you'll be able to slowly work out these things. There's nothing very difficult here. It's just the introduction of a new F table that's a little bit more difficult. Any questions? We've covered a lot of ground. Anything about the F distribution that you're not saying? All right. If not, we have reached kind of like the last slide. How do you write down model 3 in matrix notation? Things so that in chapter 3 it won't hit you all of a sudden. So you can copy this first or take picture first, then I'll explain. Okay, remember model 3 has every observation comes from a norm, first of all. Look at how I indexed it. The population is first, population 1, population 2. Every reading is normal and independent, and the two groups are also independent. How do you express this in matrix form? First, understand why this is the way it is. All right? This is reading number 1 from population number 1, reading number 2 from population number 1, reading N1, data point N1 from population 1, and so on. Okay, perhaps the one that causes confusion to people is why is this matrix like that? Okay, look at the model. Everyone that comes from here, population 1, has the same mean. Now, the fact that you all share the same mean, mu1, means you must say, oh, this times this plus this times this. So y11 comes from population 1. It has mean mu1. So you have a whole bunch of ones here and a whole bunch of zeros here to kill off this one. Then you have the reverse. These remaining observations come from population 2. So all of them have the same mean mu2, but they don't have the mean mu1. So you zero out the mu1 and you only wake up the mean. And you zoom out, you can actually see, and some people like to write it this way. My professor at grad school is the one that introduced me to all this kind of thing. What is this? This means a whole bunch of 1, 1, 1, 1, 1, 1. How long? N1 long. This is a whole bunch of ones that are N1 long. This is a whole bunch of zeros that are N1 long. The whole bunch of zeros that are N2 long, and a whole bunch of ones N2 long. You might see this in some books like that. Notice I've also introduced y beta vector. This beta vector is the vector containing all the. This is your beta. All right. This is the matrix form of the representation of this model. Vector y. This is the x. Right? This whole thing is the x matrix. This is the beta vector of that. These are all the noise terms. Okay. That's the model in matrix notation. So now we are going to immediately generalize to model 4. Model 4 is going to be more than 2 populations. You have population 1, population 2, all the way to population R. Like that. Last time we just stopped at 2. You have group 1, group 2. Now you have group 1, group 2, group 3, all the way to group R. Immediately, can you see why this makes sense? The matrix notation. Okay. So this is all the readings from population 1. Y1, reading number 1, or data point number 1, up to Y1, N1. This is data point N1 from group 1. This takes care of all your group 1 readings. This takes care of all your group R readings. So this is the most general. Sample sizes are not necessarily the same. I got N1 for group 1, N2 for group 2, all the way to NR for group R. All right. Can you see, first of all, why this matrix has become like this? One, you have ones that are N1 long, and then 0 all the way. This one is 0, N1 long. You have 1, N2 long, and then 0 all the way, and so on. Previously, our matrix was just this part. Last time, we only have N1 and N2. Now, it goes all the way. That's why I show you that slide first. Now, I'll show you this one. Right? So what's model 4? Model 4 is comparing R means where your R is more than 2. So we assume that we have a random sample from one normal distribution with another sample from another normal. Notice the sigma square are already assumed to be the same across all the groups. If you don't have that, things are impossible to do inference. Previously, when we had two groups, we assumed the sigmas are the same. Now we have R groups, we assume the sigma square are all the same. We also assume that all the y's are all independent, the groups are independent, within each group also independent. Okay? All the things are unknown. I hope you know by now a point estimate for mu I is y bar I, of course. You take the I mean as the estimate for the group I mean. Now, does anybody want to guess what does the formula for the common variance look like? Okay. So you have sigma square, right? Sigma square is the thing you're trying to estimate. I will not shine. Let me go back to my slides here. Let me show you what it was. Let me show you what this was when it was just for two groups. Okay, I want to ask you this question. Can you generalize this formula to be for R groups? Okay. So we have here's S full for when we have this is S square full for when we have two groups. Anyone know how this extends when we have R groups? Anyone want to try? What do you think? How do you extend this to be S full when you have R groups?
We just continue to
Add
adding R minus 1 times
SR squared over plus over dot NR minus 1. Exactly. Good. So the reason why I do that is I want you all to be able to see things more intuitively, and here it is. Ugh. Okay, but just did that. You see the previous formula only stopped here, right? Now it goes on. Okay. Now you may say, this doesn't look exactly the same as what we have, but it is, I know previously I gave it to you as n1 minus 1 s1 squared. That is this thing. You have to learn to be comfortable with the equivalence of this thing is n1 minus 1 s1 squared. S1 square is this over n1 minus 1. So you need to be interchangeable between the two. If you want to write this as n1 minus 1 times s1 square, you can do that as well. Same thing.
minus 2 R or minus
Oh, you're right. This should not be a typo. Sorry, I would. Is it wrong in the notes?
well, it's not written down.
Okay, I must change my. This shouldn't be 2, it should be R. Thank you. But I will go home and change this. You can see where I got this formula from. Okay, I copy it. I forgot to change it. Yes, this should be R. Thank you. Yes, that's very good. As I said, these things are not hard, but they're just very, there's a lot of formulas and things, but it's not actually hard. Okay, here's an example, and I give some R code. If you want, I will give you the R code for you to try on your own. I'll just show you the R code here. So you have some chickens, and you give them 3 different types of food to eat. This is a very small example. Data set is very, very small. Well, if you assume no variability, then you're fine. So here are the weight gains of each chicken within each feed type. I have the group mean, I also have the standard deviation. So how do you do these things in R, right? So I just want to point out a few things. This way is quite foolproof. You can learn how to do this. It's easy and works well. There are other ways, right? This is the most straightforward way I can think of and the fastest. You declare the vectors of the responses. Feed type A, 7.4, 8.6, blah, blah, blah. So that's X. You can say ABC as well. It's up to you. So you see, I gathered them as three vectors, X, Y, and Z like that. Now here's the tricky part. You have to combine the responses into a long vector. So the responses is CXYZ. Why? It means take this, append this, and then append this last one. I'm just giving you a foolproof way of doing things when people give you data and you don't know how to set up. This is the way you set it up. You make a long vector of all the response variable, X, Y, Z. This one I want to talk about. What's this factor thing? This is creating, you know what am I making? I'm making a vector of A, B, C. How many A's? As many A's as here. How many B's? As many. So length, if you remember from your statistics club, length is how long a vector is. This just means repeat A 4 times. Repeat B 4 times. I'm making A, B, C. This is a vector that tells R what groups the data come from. And look at how I fit the model. I'm using the AOV function. I know we learned LM and all that, which we can. We will use LM later. This is even more basic. Take your responses, tilde, factor. That's it. This is like LM actually. All right, you just have to create a factor like that. Ask for a summary, and then we get the famous ANOVA table that you've seen many times before. All right. So I think I will. Oh yeah, one thing. I couldn't add this. I don't know whether this is in your notes. You might need to add this. R does not give you the total line. We'll come back to this slide next time. But this is one way to do this. All right. So we will talk about the ANOVA table the next time we are together. Okay, and that's all for today. Okay. I noticed that we've done a lot of R code, and I want to show you what R we have used in class, right? To show you all, and I've also added this as a file on Moodle. So if you go to Moodle, you'll see I have R code so far, right? So I'm going to play with it with you today. One thing about R that I really like is it's now you can now run it online very easily. You don't even I can even demonstrate it without installing anything in this computer. So I'm going to show it to you a bit at a time. All right. So I'm trying to document every piece of code that I have ever ever used in class. So the first thing we ever did was to teach you how to do a simple plot of any kind of density. You set up a sequence of numbers. So this just means P is the vector of values that starts from 0, goes to 1. The step size is 0.001. That's it. So you can use all this code, you can use and modify to whatever you want, all on Google already. And then if you want to plot a graph of the value of P, and the y-axis is going to be the whatever you want to compute function of. Here I'm just computing some binomial thing, P to the 6, 1 minus P to the 4. This was in the context of finding the maximum likelihood estimated. So you'll find that this likelihood was maximized at this point. So that's how you plot any kind of thing that you want. The other thing that I want to show you is this one. As I said, all these code is found on our page. So let's look at another sequence of code. And so as I was mentioning that you can get partial credit for anything that you may not have gotten right, if you give it back to me by next Tuesday, right? And if you make corrections, try to use a different color pen or something like that on the piece of paper. And if you need any help with things that you don't understand from CD before next Tuesday, right? Okay, so I'm going through some code that I want to introduce to the class. You can find all this code now on Google, and I'm just demonstrating on my one. So I demonstrated one piece. This is another one. I want to show you how to make the normal on top work. So your data right here, you just ask QQ norm data. That's it. So again, if you run this, yeah, that's our QQ plot. Okay, now things get more interesting. And I actually spent some time yesterday developing code that would be, I wanted to give it to you because I want to show you how to do things like this, all right? I think this is more exciting. Let's say, let me show you this one. And I'll explain all these things. So, because this class, although it's not formally, it's not an R class, but I do want to teach you some R. All right, so I've got a whole lot of plots here. So let me explain the code. First of all, I wanted to show you how do you plot two QQ plots together, because you have two samples from two different populations. So this is Y1. These are your data from population 1. Y2, this is your data that came from population 2. I mean, these are sample data, but it came from different populations. So of course, we know how to draw basic QQ plots for the data separately. So you can see that if you ask for QQ norm will just give you the dots. QQ line works as well. QQ line gives you the line that you should be close to if your normality assumption is okay. To deviate barely from this line. Okay. Now, what I'm trying to teach you is to get this thing to plot both at the same time and get the lines in different colors was challenging. So let me explain why. First of all, what did I need to extract? Okay, I needed to extract the theoretical quantiles. You will find that the theoretical quantiles are different for, let me demonstrate, okay? Let's ask for Y1 theo quant. I just want to show you what I mean by this. And then Y2, I'm going to ask for these two as well. And I just want to show you what I'm doing, right? It's very important. Sometimes there are a lot of courses in Hope are very applied. And sometimes people do so many applied things, they don't even know what they do. So I just want to make sure that you know exactly. First of all, what's QQ norm Y1? So I'm teaching you some R here. QQ norm Y1 is function that produces, it gives you a plot. But hidden behind this is actually this function QQ norm provides many things that you must know how to extract. The end thing that you see normally is the picture. So you notice I'm asking for something else. QQ norm Y1 bracket 1. This actually means that the QQ norm produces things that what R calls a list. In R, the most basic data structure is a list. A list is very, very, very general. A list, this means position 1 in the list is these values. So let me explain what a list is. Imagine if you have a bulletin board in your house. What can you put on your bulletin board? Well, you can put a note to yourself. I need to buy some food or whatever. You can put a receipt. You can put a small piece of candy that someone gave you. You can, okay, what I'm going to say is a list is like a bulletin board. Whereas in R, a data frame is more general than a matrix. Okay, so a matrix, I think everyone knows what a matrix is. In R, a matrix has to be filled with numbers. A data frame is like a matrix, only that it doesn't have to be all numbers. You can have one column of, so a data frame is best described as a spreadsheet. You can have text, you can have numbers, and things like that. But it still has the limitation that it has the columns and rows. A list is the most generic. A list can contain a data frame, a vector, a picture, and all that. So a list is a bulletin board. When you want to take elements of a list, to ask for elements of a list, you put a bracket one like that. Okay? And what's the first thing that QQ norm stores in its bulletin board? It is the first thing I discovered. The first thing are the theoretical contours. Now, if you remember, these calculations remain in your notes. This is the lower, now there's 7, 8, 9, 10. There are 10 data points here. This is the lower, I think it's like not 10%, but it's the lower, it's in between. There's a lower, maybe it's the lower 8.5%, 9.5% or something like that. So basically, these are the calculations that we showed you in the work when we did this slide, where you calculate I minus 0.5 over 100 percentage, that one. Can anyone tell me why the theoretical contours for QQ norm Y2 are different from QQ norm Y1? Anyone know why? I purposely picked a data set where the sample sizes are not the same. Does anyone know why the theoretical contours for these are different? For the second data set. You can clearly see there's more values here than here. The reason why they're different is because the sample sizes are different. One of them has sample size 12 and one of them has sample size 10. So when you have a sample of size 10, the theoretical contours will be divided into 10 equal parts. If you have a sample size of 12, then each one is divided into 12. The contours have to be 1/12 each one. So that is why these apportioning are different. Okay, they are not the same. So okay, so what I want to show you is how you extract these things out. Now you look at how I plotted these things. The first thing is, because this came from a list, there's this irritating thing here that shows you that it came from a list. It's like it plucked it from the bulletin board. And one thing about R is the concept of recasting a data type. Because it came from a list, you use unlist to take away the list structure and to force it to become a vector. This is important. If you don't put these things and just take this inside, it's not going to work. It's like it has been contaminated by coming from a list. It remembers it's part of the list. It's not a vector. You have to vectorize it. So R is like that. So unlist is like to wash something and make it not a list anymore. And then you make it into a vector because the plot command needs vectors. As long, if you had typed this by hand and not plucked it from a list, R will be able to plot it for you with no problem. But because I wanted to save some time, I extracted it from a list. And that's why this happened. So you have to unlist, then do a as dot vector. This is easy to understand. As vector means make whatever this thing that was a list that was washed clean from being a list into a vector. What do I put on the other axis? The other axis is obvious, is the data. So that's how you plot this kind of thing. So let me explain. Why must I have x lim and y lim and all that? This just means I want to prepare my graph to be between -2 to 2 on this axis. I want my y limit to be between 100 to 50. Where do these numbers come from? They come from the data. You want to make sure that your graph will cover everything that you want. Why is this important? If I didn't do this, it will work, but it will just base your plot on the y1 data set. And it will make it quite narrow. your Y2 will not completely flip because your Y2 data was Y2. So this requires a bit of checking on your part. If you want to plot, you must not ever plot two things at once, you know. So you have to make this plot large enough so that and you notice here, I have to use plot once, then you use lines. If you put plot again, the old plot gets erased. Or it's like that. You call plot to prepare the plotting surface. It draws the first thing that you want. Add on more points by saying lines. The funny thing is you use lines, but I want dots. So you kill the line by saying I don't want a line. Line type equals 0. Type equals O just means I want you to plot circles like that. Color equals green, that means no explanation. So you can play with this code if you are trying to generate your own QQ plot. But eventually, if you do these things, then you see what I did? After I plotted this together, I can then add a QQ line and then a QQ line. It understands to put those things onto the plot like that. That is how you get this. It took a little bit of a coding to get this right, but that's how it is. So now you have the code, you can adapt it to any number of data sets that you have. And this actually is a good way to go back to where we were the last time. So these are code that I wanted to show you. They are all on Moodle. You can go use it, play with it, and see. All right. Okay, so where were we in the slides? So the last time we were talking about model 4, where we compare more than two groups. So we generically say there are groups. The assumptions are always important. We assume that all the data come from normal with this mean. They are all independent. And every group is also independent from each other. We also assume that they have a common sigma square. And if you remember from our last class, from the last time, what we did was we introduced the point estimate for the variance and things like that. This is called the S squared pool, if you remember. And you all correctly pointed. See, I've been so busy, I forgot to correct the typo. This one should be not too. So this is just combining the information from every group's variable. Okay. Then I believe we stopped on this slide. I gave you a practical example. So you have different feed types that you give to chickens to eat. This is a very, very small sample size, but it will serve our purpose. Every feed type has 4 chickens inside. There is a sample mean and sample simplification like that. I've given you some code. You can use this. You can also use another code which I'll show you now. All right. This is also on Moodle already. So the code that more commonly is used is to use this function. So let me erase all this. Oops. Okay, that's gone now. So let me get the last part. Now, this data is not the same as the chicken data, okay? I'm just giving you generic code that you can use to form a model 4 kind of thing. Okay, so look at what I've done. Here's the code that I have. You have 3 groups of data. Data from group 1, data from group 2, data from group 3. Now, you may be given data in a file where data are long form like that, and they have power in the system. If you need help reading in a CSV file, let me know. I usually teach R in a way that doesn't require you to have R on your computer. You can use online. But the price you pay for that is your data has to be long. I realize this is not how R is done, professionally. So you probably have CSV files of your data. If you need help reading your data and modifying the code, all right? But here is data that you can use generically. What have I done? I've created a factor vector, where we have A. How many A's? Well, don't bother to count. Just say I want length y1 as many as there are people in y1. I want b as many as there are people in y2, and then c as many as people in y2. Why is this important? Because when you do model 4, you must give the response. Oh yeah, and for example, you combine all your y's. Y1, Y2, Y3. So you make a long vector which we just insert one after the other. So the model is take your response, tilde your vector. That's it. And if you have, and all of you came from classes where you did some kind of second statistics course with me, you have seen LN before. That's how you do it. Then you just ask for summary model and all these things come up. Now, we are not going to focus so much on the prediction equation in this class because we have done plenty of that in the other stats part of the plan. I want to go to the ANOVA table. Right? Notice, in a model 4 situation, the ANOVA table will have just one factor only. Why is the degree of freedom 2? Because this factor has only 3 levels, A, B, C. So less 1, you have a 2. And if you remember, the total is never displayed in the ANOVA table in R for a reason which I explained if you did 219 or 215. There are issues with unbalanced data sets. That's why it doesn't give you the total. If you want the total, then you just add this one together. Right? So I want to go back to our data set on our slides. So you find that in this one, if you use this bulk means or AOV function will also work, but I find that this is code like difficult to use LM. So you can use LM. All right. So why is this factor 2? Because there are 3 types of. So 3 minus 1 is 2. Do you see that 2 plus 9 is 11? Why 11? Because we have 12 children. 10 minus. Again, we did n minus 1. This row doesn't exist in R, you add this yourself manually. Right? Okay. So that's the sum of squares and all that. So what I want to show you now, finally the time has come because we did not do this any other steps. Where do these numbers come from? Okay. So let me show you. Okay, so first of all, how do you calculate S pooled? Right? How do you calculate S pooled first of all? Let me see if I can zoom in, okay? I can. Yes, I can. Let me shut this off. Okay. Let's take some space here. Okay, good. Now, do you see S pooled is 3.8? S squared pooled is 3.85. First of all, you know formula. I'm taking every chicken feed group standard deviation, squaring it, scaling by the sample size plus 1. So in other words, it's the n1 minus 1 s1 squared, n2 minus 1 s2 squared, n3 minus 1 s3 squared. And then you divide by the total sample size, subtract number of groups. So this gives you 3.85. But what I'm trying to tell you is this number actually is available if you give something here. So look at the ANOVA table again. If you look at the mean square residual here, the mean square residual, don't you see a 3.8 here? In other words, the square root, the MS residual is the square. Right? MS residual is S squared pool. So that's the first connection that you should make. So a few things. How is SS total found? We always just did not really talk about this in 250 or 290 or 312. SS total, yes, we add up the SS for these two. What does it actually mean? The total deviation means you are just looking at how far away things are from the graph. There's no, in other words, the computation of this is a variability measurement that does not take into account the different feed types that you're feeding the chickens. Let me explain. If you look at the formula 1659, it comes from doing this. SS total is the summation of across all feed types and across all chickens. For each feed type, you go from chicken number 1 to 4. Notice what you're subtracting, the grand or overall mean. This is the deviation from an overall grand mean. This SS total is a variability estimate. It is. It shows you how variable the chickens are from each other, but from some kind of benchmark that belongs to everybody. So SS total does not respect the different feed types that you've given the chicken. Do you see the difference? This is, I find the grand mean, and I just see the deviations of people from the grand mean. That's it. Whereas if you look at SS residual is slightly different. The SS residual is you take every chicken's growth rate and you subtract the group mean where the chicken was from. This one respects the grouping structure. Okay? And so we can see that SS factor. So in other words, what we are trying to say is this takes into account after you have grouped the chickens by their feed, this is the deviation that the model cannot explain. This is the deviation that has no model. So I'll try to go through this again. This deviation measures how far are chickens from some kind of grand overall average. No model. No chicken feed at all. This doesn't even acknowledge that there were different chicken feed. This is what's left over that you cannot explain. After you take into the account that the fact that the chickens came from different types. So this is not the variability explained by the feed type. This is the unexplained. If you remember this phrase from when you did this intro, other stats course with me. This is the unexplained. The model cannot explain the difference between the chicken in the group versus the group. It's what's left behind. That's why some people call SS residual, SS error, SS unexplained, or whatever. It's what's left behind. Residual means what's left behind. This is what the model cannot explain. The model puts chickens into different groups. And this is the deviation of the chicken's weight from its group mean, not the overall mean. And so, what can the model explain? You can show algebraically that what the model explains is a factor SS. This is explained variability plus unexplained variability is total variability. That's what's going on. It's all variability estimates. This is no model, just how different are the chickens from the benchmark. And the benchmark is built from all the chickens. This is how different are the benchmarks from, how different are the groups of each other. And this one is what's left behind after I have grouped the chicken into the different feed groups. What's left behind that I cannot explain anymore. The model cannot explain clearly. A model that is better should have this one small or big. If a model is good, or you want to compare between two models, the model that is better has the smaller or larger SS residual. If a model is good, then the SS residual should be big or small? Small. It should not be able to, and let's not speak in double negatives. You should be able to explain most of the variability. We should not have a huge unexplained variability. All right, good. So you will find that SS residual actually is S squared food, connected to S squared food by multiplying this. All right. A few things, these ones you know already from your previous stats classes. The total gap is the total sample size, that's one. the factor, the peak type is number of groups minus 1. That's why 3 became 2. Any mean square is found by taking the ratio of the sum of squares divided by the area. That's how you find the mean square. You learned this already fast. The F ratio that you have in the display is the ms of the factor of interest divided. So it's basically a ratio of explained versus unexplained. And if it is high, then your model is good. Then it means that your model explains a lot of what's going on the chicken growth rates. So that's the logic of what this is, okay? Okay. So I actually show a few of these calculations quite painfully. If you look at how you calculate the residual, you see that oh, this is very, very painful indeed. Group 1's mean was 7.4. What am I doing here? I'm just demonstrating. This is chicken number 1 is group 1. This is group 1. I am never going to ask you to do this by hand, please. So just show you what's going on. Mechanics of it. This is chicken number 2 in group 1. These are all group 1. Then you move on to chicken number 2 in group 2. That's your 34.64, and you will see that that 34.64 is what you have in your table here, 34.6. All right. So that's what's going on. Then I also demonstrate SS total, very tedious as well. This one is every chicken, you subtract the range, which of course you can simply find by adding up all the chicken wings divided by 12. If you really did this, okay, you'll find that you get 16 whatever, and this 1659 is the thing that you see in the total SS. Okay, so we have this as well. So what does a generic ANOVA table look like? A generic ANOVA table for this kind of comparing R mean situation is always like this. You have your model or treatment or factor, whatever you call it, at least 3 words are given you. There will be an SS for the model. There is the error or residual. I'm putting error because a lot of books use error. I don't like personally the word error because it makes it look like a mistake. It's not a mistake, it's unexplained. Error, residual, whatever. So this one has n minus r degrees of freedom. So there's nothing new here. We have done this in previous text classes already. Okay. So what are some hypothesis tests that we do? This is the most famous one that we have done many times. This is the global test. The null says all the means are the same. Okay? Nothing new here. When you have 2 mean comparisons, now you see all part of the same. Anyone remember what does the alternative sound like? This is revision of your earliest math class. That's right. You can either say at least one is different or not all of them are the same. They both mean the same thing. Okay. Don't write what some students in the intro class will write. New 1 is not new 2 is not. That's a subset of mistakes. Okay. It doesn't mean that they're all different. At least one is different. So as I've mentioned before, the test statistic is the F ratio. The F ratio is calculated as the mean square of the factor of interest divided by the M. And why do you reject the null if your F is large? I've explained. If your F is large, it means your explained variability exceeds your unexplained. The model is explaining. In other words, the model is saying, no, the means are not all the same. There is something going on. That's why you reject the null if your F is big. So I'll just dwell very briefly. Now, which F do you check? All right. So first, you calculate your F ratio. You will find by looking at that ANOVA table, the mean square for the chicken factor was feed factor, sorry, was 812. The residual was, MS residual was 3.8. If you go refer to the annual. So you find that your F is huge, 211. You don't even need to look at the table. You know it's going to be a tiny, tiny p-value. The p-value is going to be, yeah, the table can't even tell you. The table will just say it's just less than 0.0001. Right? Again, let me show, okay, R will give you the exact p-value, okay? How do I know this is true? Let me show you, all right? Let's do a quick revision of where we were the last time. If you look at the F table, which we introduced the last time, okay, you go to 2, 9. So 2, 9. Now you see, 0.001 even, this table already only goes to 0.001. You only need an F stat of 16.39. If you cross 16.39, your p-value is going to be less than 0.001 already. This F statistic was a 200 plus, something like that. So we know the p-value is microscopic, but that's how you get this by using the F table. All right. You compare to an F29, and you know clearly that this is something that's really small. I mean, officially from the table it's 001. But if you did a more careful search with R, you'll find that it's very, very small. So we reject the null. Clearly at 5%, of course, we reject the null because this p-value is so small. And so it is plausible that not all the names are the same and not make sense. So we go with there's very strong evidence that not all the names are the same. Which should not have come as a surprise, because if you look at the different mean weights of the chickens, one feed type definitely had a much higher sample mean. You check the data. So it's not a surprise that we ended up rejecting them. I purposely picked a very obvious example so that it jumps out at us. All right. Okay. So an explanation for why this makes sense. So I deconstruct these things and I'll go through this argument slowly. Right? First of all, what am I writing here? The M statistic is the model MS over the residual MS. So taking all the constants outside, I have this thing. So what does this tell you? This is the total variability less the unexplained. Okay. So if the null were true, then the difference between SS total and SS error would be small. Let me explain why. The null says all the means are the same. There's nothing going on. All the groups are basically the same. If all the groups are basically the same, would you anticipate that this mean and this mean will be close? Right? If all the groups are, if the feed types are not significantly different, then whether you're feeding feed number A or B or C, and your overall weight will be very close, which means this number and this number will be close. So you see, by deconstructing this thing and writing it this way, it makes a bit clearer sense why this should be the case. You can argue another way as well. SS model, if there's a lot of difference between the three tests high and so on. So there's two ways of looking at the problem. I'm just doing one way. So I'm saying the model SS is the decomposition of total versus error. And the total and error at these forms, if these are very close to the sample, then this difference is also small. That's why a small f statistic. So if the null were true, we would expect the yi bars to be pretty similar to the grand average, and therefore your SS total minus SS error would be small. And the opposite argument is also made. However, if this is not true, then some of the sample means would be pretty different, and this would make that difference large. And that's why we reject the null for large values and calculations. So you can argue this way. You can also argue using, if the means were different, I would expect my SS model to be big. Okay? I want to talk about this because it is quite important that you understand this well, because I don't want you. This is a very, very common statistical test. The ANOVA test is very, very common. So it's worth your time trying to understand it well, right? That's why I'm spending some time. Okay, I want to look at how can you, after we have done the omnibus test, they call it, the test that compares all the means. Okay, fine and good. We've rejected the null. Don't you want to know which means are different? So I'm going to teach you a very general formula, which you can copy down first. If I want to make a combination, if I want to form a confidence interval, I mean, the one that we learned in the earlier intro set classes, if I want to form a confidence interval for mu1 minus mu2, this is very generic. If I want to form a confidence interval for C1 mu1 plus C2 mu2, or doing CR mu r, what do I use? It's not hard to understand. Have a look. You take the original constants that you're interested in, C1, C2 to CR, but instead of the mu's, you plug in all the possible. That's your big point. I mean, if you remember from your intro step class, if you wanted a mu1 minus mu2 confidence interval long ago, then don't you take y1 bar minus y2 bar? So now, if you want a confidence interval for constant times mu1, constant times mu2 like that, you have the same constants, you just pop in for mu1, mu2 order, then be careful. You need the T on card, how many degrees of freedom? It follows S food. That is why when you have a two sample comparison, it was just N1 plus N2 minus 2. Total sample size minus number of groups times S4 square root all the constants squared over sample size. Why is this the case? Right? Why is this the case?